Alright everyone, so let's just get into it. So the idea here is we want to perform pressure reconstruction from particle image velocimetry. There is a lot of interest in that because technically you can do it. Technically we have the velocity measurements, which are the u's in this equation, and if you assume density is constant, or in compressible flows if you have other assumptions about maybe an adiabatic flow, you can come up with a field that only depends on velocity, which would be this function f. And then you can, well, make a statement on that the gradient of the pressure field is just this function f. And of course the natural idea here is to just perform the pressure Poisson integration, which is you take the divergence of this vector field f that you measured, and then you integrate it twice with the correct boundary conditions using the Poisson equation. And well, it turns out that, or at least that's what it seems to be reported, there's actually some controversy here, which we will discuss through the conference. What has been found is that there is some problems with the pressure Poisson integration with respect to the amount of error that comes from the boundaries when you have inaccurate measurements and you assume Neumann boundaries. So the Richet boundaries, they perform better, but then when you use Neumann boundaries, then the Neumann boundaries kind of provide too much freedom and then let the noise contamination to propagate inside of the field, leading to erroneous estimations of this pressure. So then a couple decades ago, Liu and Katz, and then Liu, Moret, and Mitchell, these are two key works where the idea was, well, we don't technically need to perform the pressure Poisson integration. We can perform the integration directly on the gradient field, so the gradient field being f. And the idea is, if you just perform a line integral, starting with a guess at some point in the boundary, you can integrate that guess through the gradient field by just dotting the line integral with the f vector field function that you just measured. And if you do that, you can perform an update on each one of the pressure nodes. And if you do that from sufficiently many directions, then you can perform an averaging process. And that averaging process should, at least in theory, get rid of most of the random noise effect. Of course, it won't do anything to the bias error in the velocity fields, but eliminating the random noise effect is already quite a big deal. So there's a few approaches that they came up with as they were working towards this, kind of defining where the origination of the rays comes from. We are going to focus on the rotating parallel ray, which is where you have rays coming from infinity, and you have just a bundle of rays at a constant angle, and you project them, and then you rotate, you project them, you rotate, you project them, and the different angles, and then you perform an integration, and that's a very brute force approach, and we're trying to come up with something a little more efficient. So just kind of an idea of what the discretization scheme would look like. So here we have an animation of what this rotating parallel ray approach looks like. So the red lines are the ray that we want to cast. But of course our domain is a grid, so we can only discretize that ray in some manner. And in this left-hand picture here, we're using any round-off, which means that you just kind of discretize the ray on a grid, and then you round it, allowing for diagonal, lateral, or vertical connections. Whereas on the right-hand side here, we're seeing another scheme where we disallow diagonal jumps and we only allow orthogonal jumps. We call this phase crossing because if you actually stop at any frame, you see that the connections only happen when the red ray crosses a face. So this red ray here crosses this horizontal face, so then we connect these two nodes and so on. So yeah, so that's the idea. And we explored both of these approaches in our paper, but we're going to be focusing more on the phase crossing scheme because it is a little more limited and the stencil is smaller and it's way easier to understand, and the math is actually much simpler. So, okay. So just so we can kind of understand what does it mean, right? So instead of looking from the perspective of the entire domain, we're going to be looking from the perspective of a single cell. So here we're focusing on the cell C, and we are looking at the bundle of rays that comes from the cell east. And all of these rays that are coming from this east cell, they are crossing the face of cell C, as you can see here in this picture. But the number of rays would be proportional, or the number of rays that actually crosses this face, because rays that would rays below this gray ray or above this other gray ray would not be accounted in the calculation of cell C. So they would not be counted for this discretization purpose. So if you see here, these rays, if you were to count the rays, the number of rays would be proportional to the projection of this face. So if the rays are shallower to this face, then you would expect less rays to actually cross if you gave any given constant spacing between the rays. So that projection is delta y cosine theta, it turns out, where theta is this angle between the connectivity between C and E, and the ray bundle angle. And what we see here is that in this phase crossing discretization scheme, whenever we have a ray like this, we're going to implement this equation, which is just the integration of pressure gradients. And you see that this equation is just saying that the gradient of the pressure, Pc minus Pe, is just the pressure gradient at that particular line connecting E to C. And it turns out we inherit a minus sign because delta E minus delta C would be, or Xc minus Xc is facing on the opposite direction, or on the minus X direction. Okay, so this would be for an interior cell where all rays are implementing this equation. But if we have a boundary cell, then sometimes we're going to be using our initial guess, and which we're going to call this superscript n for the current iteration's guess. So if the ray comes from an interior point, then we use the next iteration's value, which we use here superscript n plus 1. So this means that the blue rays here, labeled as boundary rays, they're coming from the upper boundary of E. And this means that these rays, they have nowhere to come from. They have nowhere to inherit values from, which means that we have to assign them with a guess value for the pressure at the node E, which is PEN. Whereas for the interior point rays, the same pressure E now implements an equation that uses this future value of E, which we are yet to find out. So there are two different equations, and the number of rays that actually implements each one of the equations depends on the angle theta. So let's not worry about how many of these rays are from each one of them. It's just a fact that each one of these rays has a different weight to them. So if we look at a single cell, we can perform a consolidation of this averaging process by weighing the number of equations. So let's say here we have this node east. So for the interior ray, we were going to have a weight assigned to this interior ray, or an n plus 1 iteration ray, because it uses the unknown value of the east node. Whereas when we have a boundary ray, then we're going to use the weight for the boundaries, which are the weights for the previous iteration. If we look at the bundle coming from the north cell, we can also assign weights for the north boundary and interior rays. We can do that for also the south and the west node. This would be for the phase crossing. If we had a cell centered, then we would have 4 more equations and weights. But then at the end, we're going to have essentially for all cases a summation of all of the j neighboring nodes and all of the I iterations for all of the pressure nodes and source functions f, where the subscript j for f would be the direction where it's facing, x, y, or z if you have 3D. So we don't need to worry too much about that, but the idea is that this becomes it becomes a weighted matrix equation. So just so you can kind of see how that looks like. So here we have a bunch of weights multiplying the pressures at the n plus 1th iteration and the nth iteration, and we can just assign a matrix to them, and the matrix for a 3x3 domain would look like this. So it would have 9 elements, and we can see here that we have weights populated at the diagonal and the plus or minus 1 diagonals on the north and south, as well as east and west. So in a 2D matrix, that would look like a pentadiagonal matrix. In a 2D domain, that would be a diagonal matrix, whereas in a 3D domain, it would be a heptadiagonal matrix. And we see here that all of this right-hand side is known because the pressure guesses at the current iteration are known, and the source functions are the measurements, which means that we can just perform a matrix inversion to find out the values of the pressure at the next iteration. So a little bit of a note on the weight calculation. So This weight calculation, which is the size of the projections at all of the angles, turns out to be fairly involved, and there's a lot of cases to handle. So in 2D, there's all of these integrals to evaluate, and in 3D, it's way more involved. There's a lot of calculations. All of these details are in our paper, 2024. We actually published a measurement science technology paper on this. And you can look at the details. It's very involved, but it turns out that all of these integrals are just a constant in your code, and they're not particularly difficult to calculate once you know the formulas. Okay, so all of these that we described is actually the work from last year, right, on the iterative matrix ODI. And the performance, we assessed the performance. It performs better than the rotating ray ODI because it's a kind of a continuous limit to the rotating parallel ray. And of course it does way better than the pressure-Poisson equation, which was expected. But also computationally, we implemented this code in a GPU, and it is way faster. It's about 1,000 times faster than the state-of-the-art, which was Wang et al. It's a GPU implementation of the brute force omnidirectional integration method. And we see here that we are able now to handle insanely large grids in reasonable times, although there is a fundamental issue here that this process is still iterative. So this time that I'm plotting here is actually time for one iteration, but it turns out that there is a convergence behavior, and especially for the larger grids, you may need between 100 and 1,000 iterations to actually converge to a solution. So that now becomes a problem. So then now let's talk about the content for this particular talk, which is, can we fast forward this process? So we kind of figured, right? So we have this iterative process that turns out to be this matrix equation. Here I just separated the summations in I for the for the iteration n+1 and n. And what we can do is at the infinity iteration, we can say that, well, if it's converged, then it should converge to the same value. So we can just replace that value at the infinity iteration or infinity plus 1. It would be the same value. So we do this, and then we do a little bit of mathematical manipulation that is not really the point of this talk. You can look up on ArXiv, we have a submission for that. But the idea is, okay, so we perform this manipulation, and now we have another matrix equation. And then, of course, the question is, this matrix equation, if you actually look at the details, it's underdefined, or its condition number is infinity or very large. So then, can we still solve it, right? And this is what we call the one-shot matrix omnidirectional integration method, or the OSMODI. And as I discussed, it's not a well-defined problem, but it turns out that if you use a conjugate gradient solver, you can actually solve it, which was totally a naivete of mine. I actually didn't know about all of these concerns. I just implemented the solver and it worked. But it turns out that it worked. It converts to the same solution, as we can see here in our little chart, showing that as we increase the number of iterations and we reduce the residual, we get the solution for the one shot. But it takes the same time as it takes to solve a single iteration of the iterative method, which means that we can save all of these iterations and we can do it all in one shot. So we have a very significant computational time of, well, about 100 to 1,000 times faster, which means that we can claim here that we are about 1,000,000 times faster than the state of the art, which is awesome, right? It's a very powerful solver, and I think we can handle some significantly large problems with this. So just as a little demonstration, here's a little animation of compressible flow measurements that we performed, where we have a double fin problem at Mach 2. And these are scanning PIV measurements at this grid here. This grid has about 5 million elements, and the volume is fairly large, right? And we can see all of this beautiful shock structure that forms in this double fin, which is unseen in 3 dimensions until we've done it, right? Which is really cool. But in the case of compressible flows, using the correlations by Van Oudhuizen in 2008, he has a very good description that if you just assume that the flow is adiabatic, which is a very reasonable assumption to have, then you can get temperature and then pressure from PIV by integrating this modified equation, which includes the Reynolds stresses. And then, of course, density just comes from the ideal gas relation. So this is really cool, and we were able to solve this large problem, which is 5 million grid points, took 2 seconds to solve in a laptop, which is really cool. Of course, on a GPU, but still really cool. And I'm kind of excited about this. But anyway, so there's just one last point which is really worthwhile mentioning, because it's basically the biggest point of contention, right? So when we noticed that if you look at the actual values for the coefficients of the matrix, well, when we have a grid that has delta x and delta y different, then the implementation on a 2D grid looks like this for the pressure Poisson and like this for the osmodi. And you see that they look very much the same. Here I made an effort to isolate the terms. So you see here that the x kernel versus the y kernel, they are isolated in this parenthesis. And we can see that they look very similar, but there is an extra delta x in the pressure Poisson, and you can't really cancel those out. But if the delta x and delta y spacings are the same, we're going to call that delta, then the two kernels simplify to the same equation. And this is very interesting, because it means that in the isotropic grid case, the pressure Poisson equation is exactly the same as the osmodi. And more interesting is, of course, the boundaries. So here I'm showing the west boundary, and we can see that if you have a west boundary, then we basically drop one of the terms, and then instead of having a quarter grid, then we have 1/3 kernel instead. So of course we consider then maybe we can extend this to unstructured grids. I'm going to be very brief here. This was inspired by the video by Tribulot and Brown, where he discussed about the Cauchy's problem, where you calculate the average shadow of a cube coming from different directions, which is exactly what we're doing here. And it turns out that you can generalize this for any convex solid. And if you do that, then you can derive a different matrix equation for unstructured grids, both 2D and 3D. We actually tested it, and it works surprisingly well, actually. So we're looking into performing more implementations on this direction, especially for pressure from PTV, right? So if we have particles at the center of each one of these grid points, then we can tessellate it with an unstructured mesh, as we're showing here, and then hopefully we can also get pressure from PTV instead. Okay, so in conclusion, we extended this rotating parallel array to this iterative matrix ODI method. This was already very efficient, but then of course the natural extension is to do a one-shot implementation. We've done that. Works wonderfully, even though it shouldn't, because it's an ill-defined problem from a matrix operation. The condition number is too high, but it still works due to the conjugate gradient. And then we observed that the performance improvement is about 1 million times faster than the original ODI, which is really nice, because now we can work with very large 3D grids. We have a demonstration here. And then, of course, we can extend this to unstructured grids, which has really good potential for PTV applications. So I appreciate your time watching this video. And if you want to have any questions, then yeah, shoot a comment below, and I look forward to your comments.